Welcome students. In this video we are going to talk about something called a Laplace equation, right? So last video we have already looked at what Laplace equation is, and now we are going to look in depth about all the properties it satisfies. So essentially we have this equation Laplacian of u equals to 0. Yeah, you can also look at this sort of thing. They write it like gradient square u equals to 0. This is mathematically incorrect, okay? But generally in engineering text they actually write it like this, so you can do that, absolutely no issues. Okay, so Laplace u equals to 0, and this it will be in some domain D, or for now I am writing it to be omega. So omega is a domain. What is a domain? It is an open and connected set. It is a domain in Rn. N is greater than 2, equals to 2. So n equals to 2, if you want you can just put it for n equals to 2, absolutely no issues. But I mean for any dimension this works, whatever I am doing. So you have this information that you are looking for a u which is defined from, so I will write that down later. So essentially you have a u which is defined from omega to r, and you want to find out and which says that Laplace u equals to 0, and you want to find out if there is such a u. That's the point. So this is called the Laplace equation, right? Laplace equation. And if you remember, we also talked about the Poisson equation, which is given by Laplacian of u equals to f. Yes, this is called the Poisson equation. Okay. Now, so of course this is also in omega. So all of these equations are in omega. Now, what is this u? So basically that's your unknown, right? So see here, u from omega bar to r. Omega bar is the closure of omega, right? I will explain to you again. So this is essentially, what is it? So you see, if you take x, so let me do it here. Let's say if I'm starting with the x in omega bar, yeah, omega. So you have u of x that will be defined, right? Now you take x naught which is in the boundary of omega, right? So omega bar is basically the domain omega which is open along with the boundary of it, right? So think of it like this. Let's say if you have a open disk, yeah, open disk which is mod z mod x less than 1, and then the boundary of it will look like mod x less than equals to 1, right? Equals to 1. So that's the boundary. Now the thing is, if you add those two up, so basically you take all the points here along with the boundary, that will be your omega bar in this case. So if this is omega, that is your boundary del omega, and then omega bar is omega union del omega. That's what. Yeah. Okay. Now when we say that we are basically looking for a u from omega bar to r, it means that u is defined for all points x naught in boundary. So of course u is defined in omega, and it's also defined for all points in the boundary. So we are looking for such a u, okay, and this omega is a given, given set. So it is already written, right? The domain in omega, right? So u from omega bar to r is the unknown function. Unknown function. Yes. Okay. And you see that f of course will be given to you, and f will be given to us. So it's given. Yes. And if you want to find out, see, f is from what to where. So this equation will look like this: Laplacian of ux equals to f of x, right? Yes. So this is for x where u is defined, yeah. So for such x, so basically f will be defined from omega bar to r. Yes. So we are going to use this sort of ideas. Yes. I'm not writing that part up, but it is very clear here. Okay. Given function. Okay. Now what is Laplace of u? If you remember, Laplacian of u in our definition is this: u x1 plus u x2 x2. Yes. So you take all this double derivative, which is like xn derivative, xi, and you add it up over all the variables. So xn, right? So that's your Laplace equation. This is also written as gradient squared u. This is abuse of notation, but this is fine. Okay. Now the definition, let me write it down. Definition of what? Definition of a solution, right? We already talked about it, but still, see, u is in C2 of omega bar, okay, that satisfies 1. So let me write down the Laplace equation is 1, Poisson equation is 2. Satisfies 1 is called an harmonic function. We talked about it in the last video also. It's called a harmonic function, right? So what does it mean? It means that you are basically looking at a function such that Laplacian of u is going to be 0, and on the boundary it is I mean, if some boundary data is given, it will satisfy that boundary. So here there is no boundary data is given, so you just need a function which is twice continuously differentiable and the Laplace of u equals to 0. As an example, you have talked about this example, right? Some constant times a, so let's say u of xy, x1 x2, yeah, this is the function. X, this is x is x1 x2, 2 dimension. So that you can just write this thing up, a of x1 plus b of x2, and this is a function from r2 to r, right? And this is going to be harmonic. You can easily check it, is absolutely no issues, right? Okay, so that's a harmonic function in 2 dimension. You can just do it in higher dimensions also, no issues here. Okay, so that's your harmonic function. Now let's look at the physical interpretation of this. Physical interpretation, because the thing is, you see, we are essentially looking from at it like I mean, not like purely mathematical thing. There should be some ideas coming from real life, right? So what is it? So let's say that we are denoting u, the unknown function. Let's say this denotes the equilibrium, the density, okay, density of a chemical concentration in equilibrium. Okay, so what is this? Essentially think about it like this. You see, you have seen those mocktails, right? So essentially what happens is there are like 2 different kind of syrups, different colored syrups. We actually add it together here, and you can see that there will be these layers, right? Very beautiful looking layers of different colors. Yes. So essentially, see, when you are just pouring, so let's say when the waiter is just pouring that one liquid over another, then with time, so there is this I mean, you know, chemical reaction which is going on, right? So it is mixing with each other, and after some times what happens is it actually I mean, comes to an equilibrium. So it does not mix anymore, and what happens is it actually creates a very nice, you know, looking drink. Okay, so you see, the thing is, and that drink, you do realize that there will be a difference in density. Yes. Okay, so let's say that u is that function which actually denotes that density of a chemical concentration and when that concentration is in equilibrium. Yeah. Okay, so then this is just an example. There are other many different examples of this. This is just an example. So then if let's say v is any smooth sub-region within omega, clear? Then the net flux, okay, of u through the boundary, through del v, yeah, is 0. Net flux is how much the density is changing. So let's say that you have this glass, right? You have this glass and it is in the, I mean, as I have already explained, it is in equilibrium something. Now you take a small region of it. This region is not one dimensional, 2 dimensional region. You understand? Think of it like a proper, you know, 3 dimensional region you take within the glass, within that confines of the glass. So essentially, let's call this V. Yeah, this is a 3 dimensional region. I hope you can understand this one. Okay, so now the point is this. You see, if you look at the boundary of V, right? Now the thing is there any change in the density across the boundary? No, right? Because it's in equilibrium, chemical equilibrium, right? Okay, now the thing is this. So what that mathematically says is over the boundary del V, if you talk about the integral of it, so basically f dot gamma ds, that is going to be 0. Yeah. So what does it mean? It means that okay, and what is what is the f? Let me write it down. F is the flux density. So essentially what it is saying is this, and gamma is the outward normal, outward normal. So since there is normal, so you see, since the flux, so basically there is the net flux, okay, so across this boundary is 0. It means that the if you take the flux density at in a given point, so basically let's say in a given direction eta, okay, on the boundary of course. And the thing is, if you add all these points up, what's happening, since the net is 0, net flux is 0, right? So it is integral over del v f dot gamma ds is going to be 0. Clear? Okay, so now once this is 0, you see, you can use Green-Gauss theorem. Green-Gauss theorem, I hope you remember Green-Gauss theorem. Okay, Green-Gauss theorem. And what does it say? Essentially, it's basically your integration by part formula. It says that integral over v, divergence of a vector field v, f in this case, dx is equals to integral over the boundary f dot n ds, f dot gamma ds. And in our case, this is going to be 0, right? That's what we have already. So what does that mean? It means that integral over a volume v, clear? And so whatever that domain we started with v, the divergence of f, that is going to be 0. That's what we are getting. And where? This is in so you see, and so what I'm saying is the divergence of f, that is basically some function, right? And that function, if you integrate it over any region v, see v, there is nothing special about v, is any smooth, see, it is any smooth subregions within omega, right? So essentially what happens, it actually says then divergence of v has to be 0 in omega, right? Because otherwise, if it is not 0 in omega, it has to be positive or negative, right? And in that, what you can find is you can get a neighborhood where, it is going to be a contradiction. So basically, you can say that in the whole domain omega, this is going to be 0. Okay, the divergence, of course. And why this is true? Because since v is any smooth domain, so v is arbitrary, right? See, generally speaking, what is the idea again? Let me explain. See, f is basically a vector field, and without loss of generality, you can just assume this is a continuous vector field. At least in our case, definitely it's going to be continuous vector field, right? So divergence of f, and not even continuous, it will be continuous differential basically. So divergence of f as a function is basically a continuous function. Now the point is this: if let's say if divergence of f, so if divergence of f is not 0. At some point, so essentially in that point, around that point, you can have a small neighborhood around that point. So let's say the x0 is that point. So around x0 you will have a small neighborhood where divergence of f probably it is negative or positive something, right? So if it's not 0, let's say it is positive. So essentially what happens is at the point x0 there is a neighborhood where it will be positive. That's basically your neighborhood property of continuous function. Okay, so once that is there, then if you take your v to be that particular neighborhood, if you integrate it, that is going to be non-zero, right? Now that will give the contradiction to this. So essentially you understand that it has to be 0 over the whole domain omega, right? Now this is physically what is happening now, physically speaking, okay, this flux f, right? So the flux f, this should be proportional to the gradient, should be proportional to du, right? Or gradient u, whatever you want to write it. We also write it as gradient of u, absolutely no issues. But points in the opposite direction, right? In the opposite direction. I will explain to you what it means. Let me write it down. Opposite direction. Okay, what it means is this. See, the thing is this, the flow, where should the flow be? Think about it this way. See, the flow generally, yes, so basically what is the, see, the here we actually said that f is the flux density, right? Now the thing is this, think about it, the density, yeah, how does it change? So basically that change is the flow, right? And the flow will be from the region which is on a higher concentration to the region where it has a lower concentration. So from higher to lower, the flow changes, right? Yeah. So you see, since the flow is from the region of higher concentration to lower concentration, so this f will be proportional. So these are basically same thing. will be proportional to gradient of u, but it will point to in an opposite direction because of this change in from higher to lower, right? So therefore f will be proportional to gradient u. So basically I can write it as some constant times, let's say some constant c times d of u, correct? And this c, sorry, this c is positive. I hope this is clear. Okay, gradient u is again what? See, u is the density, yeah, and gradient u is the change in the density. So basically the flux f should be proportional to that, but the change in the density, where it is coming, not from lower to higher concentration but from the higher to lower, so we have a negative sign. Clear? Okay, so now if you if you substitute this particular thing here, what you are going to get is you have the Laplace equation, and it will be given by divergence of gradient u, gradient or du, whatever you want to write it, that's just a notation. And this is nothing but let me write it properly so that you understand. See, what is divergence? Divergence is basically del x1. So okay, so let me write it this way. See, first of all, let me write down what is divergence of a vector field. So let's say f is a vector field, given by f1, f2, fn, right? So divergence of f is nothing but you take the first f1 and take it with respect to x1, and then take the last fn, take it with respect to xn. You understand? So if you write it here, it becomes u x1 plus it goes on del xn u xn, right? So you do realize this is nothing but the Laplacian of u. So essentially the equation, so from here what you get, therefore you get the equation which you get is called Laplacian of u equals to 0, okay, in omega. So that's your Laplace equation. Okay, now see this, as I told you, there are like many different things which in these models, and don't think it's just a chemical concentration. So let's say if u models, so if u models chemical concentration, as we have already seen concentration, okay, then this equation, this one, star, then star is called the Fick's law of diffusion. I think you have heard about it, right? Fick's law of diffusion. In your physics class, I hope you have heard about it. Okay, now if it models the temperature, it can model the temperature also, right? So think of the similar sort of thing, but the temperature increasing, the heat flow, basically that will actually change the temperature, right? So basically the flow of the temperature, that is what you models. So if it is a temperature, then star models. What does star models? Models the Fourier law of heat conduction. Clear? Okay, now let's say that it can also model, electrostatic potential, right? Electrostatic potential, okay, and then star models, in this case star models, okay, Ohm's law of electrical conduction. Yes, so you can check with your physics books and confirm that whether what I wrote is fine or not, but of course this is fine. So what I am trying to say is this: see, this is not some like purely mathematical thing. There is like a huge physical interpretation part of it. Yes, so that's your Laplace equation. Okay, now what I'm going to do is I'm going to write down some mathematical theory behind it. Okay, so we'll do something called a fundamental solution of it. We try to find it, fundamental solution. So what does that mean? Let's just think about it. Solutions. Okay. So fundamental solutions are basically what I mean. You see, there are a lot of other mathematics which is involved here, like invariant random notation and all those things. I mean, forget about that. So basically, what I'm trying to say is this: let's say you have this equation Laplacian u equals to 0 in Rn. In Rn, huh? There are many mathematical insights about it, but for this course we are not really interested in that. Clear? Okay, so since Laplacian u equals to 0, let's say we start with that in Rn, right? And what we want to do is we want to find the radial solutions of it. What is a radial solution? Radial solution is, think about it like this. Let's say that in 2 dimensions the domain is R2. Clear? So this is your domain, huh? This is your domain, and let's talk about the circles on the domain. So corresponding to this circle you will have, so let's say take one point here. So u at that point will have some value. Again you take another point on the same circle. Yeah, let's say this is x0, this is x1. U at the point x0 and u at the point x1 may not be same, right? Yes, of course it cannot be. I mean, not cannot be, it may not be. Okay, so what happens is that we want the function to be always it should take the same values on circles. So basically, let's say you have a circle of radius r. The value of the function should be constant on r. So for example, let's say mod x square. If you take this sort of function, you can see that on the let's say on the circle x mod x equals to, let's say, capital R, this function always takes r square. On mod x equals to r plus, let's say, r1, this will take r plus r1 square. Right? So for every point on this particular circle, this function will have a constant value. You understand? That's the thing. But the function itself is not constant. Yeah, so that is called a radial function, right? So you see, Laplacian of u equals to Rn, we are just looking for radial solutions of it. Yeah, so what do we do? See, the solutions which you are looking for is u of x should look like v of r. Yeah, where r is what? It is basically mod x. So which is x1 square plus xn square whole power half. Okay, so this is your, so define u of x equals to v of r, where this is this. So essentially what am I doing is this, let's just, we are assuming that, let's say there is a solution u of x, right? And the thing is, we want that solution to have some particular properties. What are the properties? We just want it to be looking like some function of r. Yes, what is r? Mod x. That's the thing. Okay, now if that holds, you see, first of all, let's just look at this particular thing. What is del r by del xi? Yeah, see, r is a function of x1, x2, xn, right? See, r, if you think about it, it's basically a function of x1, x2, xn. If x1, x2, xn changes, r also changes. Clear? Okay, so if I'm looking at the derivative of r with respect to xi, so basically what am I doing? As I told you, r is a function of x1, x2, xn's, right? Yeah, so you do realize that if I'm changing one particular variable, r is also going to change, right? So essentially, if I am looking at a particular direction, let's say xi direction, and I want to see what is the change in r in that direction, that I can do, and that is basically nothing but x1 square xn square whole power what is it, minus half times 2 xi. Is it okay? So that if you calculate it, it becomes xi by r. Okay, and of course x, I am assuming it to be non-zero. Yeah, otherwise r is going to be 0. Doesn't make any sense here. Yeah, okay, so del r by del xi looks like this. Now what about uxi? Let's look at uxi. Uxi will look like this. It's basically a chain rule, right? Uxi. So u is a function of v. So uxi, if I'm doing it, it's basically derivative of v with respect to r. So that is let's say dv by dr, and then you have with respect to r dv by dr, and then I have to take the derivative of r with respect to xi, right? So it is del r del xi. Is it okay? So that's your chain rule, right? So this will, if you want to write it, it basically the derivative of v with respect to r, and then dr by dxi. Yes, so which is xi by r, xi by r. I hope this is clear. And then similarly, what is uxi xi? Why we are finding uxi xi? Because we want to substitute it in Laplace u. So that will look like this, v double prime of r. This I want you to check. Please check. Okay, v double prime of r xi square by r square plus v prime of r 1 by r minus xi square by r cube. Is it okay? So that's what this uxi is. Now you see Laplace u is basically the sum of this. So basically we have to add those things. So this is for I equals to 1 to n. For all I, this is true, right? Now basically for Laplace equation, I just have to add it. So what is Laplacian of u in this case? It is nothing but the summation of this, which is v double prime of r plus n minus 1 by r and then v prime of r. Yes, I'm just adding this thing up, and this you can easily see that this is going to be true, absolutely no issues. Now since Laplacian of u is going to be 0, that is given to us, so it means that this is if and only v double prime of r plus n minus 1 by r v prime of r should be 0. Now if you choose v prime of r to be some function phi of r, yeah, then this equation becomes phi prime plus n minus 1 by r, which is basically a constant, times phi equals to 0. So that's the first order ODE, which we know how to solve it. Yeah, so I am just writing down the solution. So if you just use the usual way of solving it, if r is positive, okay, because you see we have assumed r x is not 0. So if x is not 0, r is definitely positive. Okay, then what do we have? We have v of r. Yes, that is going to be a constant c1 times log r plus c2. Okay, and this is for n equals to 2, and it is going to be b by r to the power n minus 2 plus sorry, let's write it c1 plus c2. So this is for n greater than equal 3. Okay, so what we can do is essentially we can solve this equation for r equals to 2, n equals to 2 and n greater than equal 3, and we can see that those are the things. So with this, what we can do is we can define the definition, the fundamental solution with this definition. So you see the function phi of x, which is defined as 1 by 2 pi log of mod x for n equals to 2 and 1 by n minus 2 some volume of the sphere alpha n. So basically that's the normalization constant. Think of it like this: mod x to the power n minus 2, 1 by mod x to the power n minus 2. So this is for n greater than equal 3, right? So that is defined for x in Rn, okay, minus 0. That is defined for x in Rn minus 0, and this is called the fundamental solution of the Laplace equation. It's called the fundamental solution of the Laplace equation. I hope this is clear to you, right? So this is just an of Laplace equation. This is a stepping stone of studying Laplace equation. So what we did is this: see, we didn't knew that if there is a solution or not. What we did is actually we assumed that, let's say there is a solution, and the property of a solution is it should satisfy the radial. So basically it should be a radial function. Once we assume that, we can actually calculate the whole thing down, put it in Laplace u equals to 0, and you get this, right? So since r is mod x, you can just replace it, and this c1 and c2 we are just replacing it like this particular constant, because I mean this is normalization constant, it's nothing much actually. So with these constants we basically say that this particular equation solution, this is a fundamental solution of the Laplace equation. Of course, it is satisfied for x in Rn minus 0. Yes, okay. So now Rn minus 0, right? So now what we will do is essentially we'll look at one particular thing. So I just want to explain this particular thing. See, what happens is this: if phi is the fundamental solution, okay, if phi is the fundamental solution of Laplace u equals to 0, okay, then if you look at the gradient of phi x, okay, that is dominated by c by mod x to the power n minus 1. And if you look at the second derivative of the fundamental solution phi x, of course this is not x not equals to 0, this can again be dominated by phi mod c by mod x to the power n. Okay, this x is not 0 here. Okay, so essentially what this actually says is the first derivative of this fundamental solution is always bounded by 1 by mod x to the power n minus 1, and the second derivative is always bounded by 1 by mod x to the power n. Okay, so with this I am going to end this lecture, and in the next lecture we are going to talk about a very important thing which is called a maximal principle, and then we will look at some properties of the maximal principle. Thank you.